Hello everyone, and welcome to the new episode of our series of solving LeetCode Daily challenges. And today we are going to solve a problem called Find Eventual Save State, which has a medium difficulty. So let's read the problem statement. So we are given a directed graph of n nodes, which is represented by this array code graph. And we define node as a terminal node if it doesn't have any outgoing edges, and we define a node as a safe node if every possible path starting from that node leads to a terminal node or another safe node. And also by definition, our terminal nodes are considered to be safe nodes. We need to return an array of all of the safe nodes, and we need to sort this array. Okay, let's look at the constraints. The number of nodes in our graph is up to 10,000. The number of edges in our graph is up to 40,000. And we have some other nice conditions that describe how the graph is represented. And our graph may contain some loops. Okay, so to solve this problem, let's start from the example. Suppose we have a graph that looks like this, and we will find all of the safe nodes in an iterative manner. So at the beginning, we can tell that node number 4 is a safe node by definition because it's a terminal node. And that's the only terminal node that we have. Then we can tell that node number 3 is a safe node because the only path starting from node number 3 leads to a safe node number 4. Then we can tell that node number 2 is a safe node because all of its passes lead to the safe node. We have a path 2, 4, we have a path 2, 3, and we have a path 2, 3, 4, and all of them lead to the safe node. And in the end, we can also tell that node number 1 is a safe node because once again, all of the passes starting from 1 lead to the safe. So from this, we can actually construct an idea of a solution. We will add the nodes to some set of safe nodes in an iterative manner. At the beginning, we will add terminal nodes to this set, and then we will process all of our nodes, and we will take a look if our current node only contains edges that leads to safe nodes, then we can add our current node to this set of safe nodes. So if the node has only edges that lead to safe nodes, then it's also safe. And by this definition, our nodes 5 and 6 will never be safe. And now I'm going to formally prove this statement. So if you like proofs, please stick around, and if you don't, please move to the next chapter. So our statement goes like this. A node is safe if and only if one of two conditions apply. Either the node is a terminal node, then by problem statement, by definition, it's a safe node. Or all of the edges of a node lead to another safe node. Okay, so we need to prove the statement. So let's first prove that nodes for which neither of these conditions apply is not safe. So suppose we have such a node. This means that a node has an unsafe neighbor, meaning that there is an edge from this node to some unsafe node. Then we have a path of length 1 that does not lead to a safe node, which means that the current node is not safe. Okay, now suppose that all of the edges of a node lead to another safe node, which is our statement number 2. So what can we say? We can say that all of the paths of length 1 lead to the safe node by our assumption. And now let's consider the path of length k, where k is bigger than 1. We can split such a path into two smaller passes. One path of length 1, which will lead to a neighbor of the current node, which by our assumption is a safe node, and a path of length k minus 1. So this path of length k minus 1 has to lead to a safe node because it starts in a safe node, and by our definition of safe node, it should also end in a safe node. And otherwise, our neighbor wouldn't have been a safe node. And yeah, basically it's like a proof by induction, you can say. And yeah, that's a formal proof. Let's take a look at the implementation of our solution. So we will need to have a couple of data structures to efficiently implement our solutions. First of all, we will calculate a list of integer called degrees, and it will have size of exactly n, and the is element of this degrees array will show how many edges come from the node I and go to an unsafe node. And this means if the degrees of some node is equal to 0, then this node is a safe node. So at first, we will just calculate this array or list as the number of edges that go from this specific node. So degrees 0 basically shows us how many edges goes from node 0. And we will also have a queue of the nodes that we consider safe. And at the beginning, we will just add a terminal node to this queue because they are by definition safe. And then we will do the iterative process just as like in our example. So we will pull the item from the queue. We will add it to the resulting list because all of the items in this queue are supposed to be safe. Then we will iterate through all of the edges that end in our current node. And to do this effectively, we will build this list, which is basically a reversed adjacency list of our graph. So we are iterating through all of the nodes that have edges that start somewhere and end in our current node. And for all of these nodes, we will simply decrement its number of degrees. So suppose we have an edge from V to U, from V to current node, and now we say that current node is a safe node, then the number of edges from V that lead to an unsafe node should be decremented by 1. And that's exactly what we are doing here. And if now we see that degrees of V is equal to 0, or here I call it edge start, then we can say that edge start is a safe node, and we can add it to our queue. And in the end, we are simply sorting the list and returning it. And that's pretty much it. Okay, so what's the complexity of our solution? The complexity of our solution is big O of n plus m, where n is the number of nodes and m is the number of edges. Because let's look why is that. So here before our main loop, we do some operations which consists of either n or m smaller operations, atomic operations. So basically, the complexity of this part is big O of n plus m. And in our loop, we will consider every node at most once. And in this loop, we will consider every edge at most once. And because of that, our complexity is big O of n plus n. Another thing that I'd like to mention really briefly is the concept of topological sorting. So some of you might notice that this problem is very, very similar to a topological sorting problem. And yeah, I think it's quite possible to solve this solution with the algorithm of topological sorting. Basically, we perform the topological sorting of our graph, and then we iterate through our nodes in the order of topological sorting, and we simply, actually in the reverse order of topological sorting, and we check if this condition that I've stated, that all of the nodes, all of the edges from a node should lead to the safe node, if this condition holds. And if it does, then our node is safe. And if it doesn't, then it's not. So there is no need in this topological sorting solution to keep this queue and do stuff like that. Okay, guys, Thank you very much for your attention. I hope this solution was useful for you and interesting. And if you liked my content, please press like, subscribe, and I will see you around. I will leave all of the necessary links, such as link to my code and link to the article about topological sorting, in the description of this video. So yeah, have a good day, and it was nice talking to you. Bye bye.